Very good morning, friends. We were dealing with various basic concepts of organic chemistry. We have seen that organic compounds are having different bondings, and this bonding arises due to the sharing of electrons that they have covalent bonding. They can also have coordinate bonding, and this bonding, if it differs, then can give rise to a concept called as isomerism. Today's subject of discussion is isomerism in organic compounds. What is this isomerism? What are these isomers? Isomers are those organic compounds which are having same molecular formula but they differ in their structural formula. Means molecular formula will be same but they differ, their structure differs. The isomers, the compounds, if they differ in their bonding connectivity, then they are isomers which are called as structural isomers. The another name for structural isomers is constitutional isomers. These are the compounds which differ in their structure by differing in their bonding connectivity. And there are another set of isomers which they differ in their spatial arrangement. And those isomers which differ in their spatial arrangement are called as stereoisomers. Their another name for stereoisomers is configurational isomers. Those isomers which differ in their spatial arrangement are stereoisomers, and those which exhibit stereoisomers are called as stereoisomerism. The structural isomers can be classified into six types. The first type of structural isomers are chain isomers. The second one, positional isomers. The third one, functional isomers. Ring chain isomers, tautomers, and metamers. What are these? Let us look into it. The first variety are those compounds which exhibit chain isomerism. As the name indicates, chain isomerism are those isomers which differ in the arrangement of carbon chain. The butane can exist in two forms, N-butane and isobutane. The N-butane stands for normal butane. Isobutane is the branched chain of N-butane. Both N-butane and isobutane has the same molecular formula C4H10. The N-butane, they are arranged in a single chain. 1, 2, 3, 4. One carbon is attached to another carbon in a continuous manner. In isobutane, the last carbon, instead of attaching to the third one, it is attached to the second one. This is called as isobutane. N-butane and isobutane exhibits chain isomerism. And these are chain isomers. Another variety of structural isomers are those which differ in the position of their functional groups. They have the same functional group, but the functional group's position only differs. Then they are said to exhibit positional isomerism. 2-pentanol and 3-pentanol, 2 hexanol and 3 hexanol, and so on and so forth are various examples. The hexanol has the same molecular formula C6H14O. The 2-hexanol, the functional group alcohol, is at the second position. 3-hexanol, it is the position of the functional group is at the third position. There are another set of isomers which have this different functional group. In positional isomerism, they have the same functional group, but the position of that functional group differs. Whereas in functional group isomerism or functional isomerism, the functional group itself differs, but still it maintains the same molecular formula. A very fine example for this is ethanol and dimethyl ether. Both have the same molecular formula C2H6O. Ethanol structural formula is CH3CH2OH. OH is the functional group present in it. The dimethyl ether is CH3OCH3. It has oxygen as the functional group to which the two methyl groups are attached. This is an example for those compounds which exhibit functional isomerism. There are another set of structural isomers where the nature of the bonding changes. One exists in cyclic form, another exists in open chain form. They are called as ring chain isomers. Example for this is cyclopropane and propene. They have the same molecular formula. Cyclopropane has 3 carbons attached in a cyclic or connected in a cyclic manner. Whereas propene has a normal chain which are two carbons are connected with a single bond. The next 2 carbons are connected with a double bond. It is propene. Propene and cyclopropane are example for ring chain isomers. There are another set of structural isomers which are called as tautomers. Here, the position of the proton and double bond in the structure are in dynamic equilibrium. These are compounds, they exhibit in both the forms. It is something like God. Ram is also God. Rahim is also God. For Hindus, Ram is God. For Muslims, Rahim is God. But both are gods. Ram and Rahim, they are in equilibrium for Hindus and Muslims. Here, the position of the proton and the position of the double bond will be differing. And these compounds, they coexist with each other. Who is God? Ram is also God. Rahim is also God. They coexist with each other in Hindus and Muslims. Means they are in dynamic equilibrium. The another name for tautomerism is desmotropism. One of the variety of tautomerism is keto-enol tautomerism. These are the tautomers in which the compound exists in both keto form and enol form. The carbonyl compound exists in keto form and also enol form. One example I can give is acetone. Another example is acetoacetic ester. Both exist in both keto form and also in enol form. Acetone CH3COCH3. This is carbonyl group. The hydrogen here in the CH3 group gets detached and attached to oxygen, and it has to maintain its divalency. That's a pi electrons moves towards this carbon, and the carbon tetravalency is maintained, the oxygen divalency is maintained. Here you see carbon is one, two bonds and two bonds with hydrogen. Its tetravalency is satisfied. Here oxygen, one connection with hydrogen, another bond with carbon. That's why its divalency is maintained. That's why this is stable. This acetone and acetenol, we can call it as acid ene group and ol group. Acetenol. The acetone exists in say in the acetone ketonic form and enol form. Another example which we can quote for keto-enol tautomerism is acetoacetic ester CH3CO CH2CO OET. Here this is in keto form and it is also existing in enol form. On and enol. Another type of tautomerism which we come across in organic compounds is enamine-imine tautomerism. The amine exists in both amine form and imine form. Imine is in ene. The double bond in enamine converts amine with a double bond, enamine converts into an imine with a mobile proton. Here you see 2-aminopyridine. The amino group is in amine form, right? This can get, and this nitrogen in the pyridine ring is in imine form, ene form. This is having ene and amine. That's why it is called as enamine. This double bond shifts between carbon and nitrogen here, and the hydrogen here shifts towards this nitrogen to give enamine. Amine and imine. Enamine to imine form. The enamine and the imine form coexist with each other. The another type of tautomerism is lactam-lactim tautomerism. The amide can exist in lactam form and the imidic form, that is lactim. That's why they are called as lactam-lactim tautomerism. Amide, carbonyl group and amine group, the nitrogen hydrogen bond breaks and that bond is found between carbon and nitrogen. It becomes ene and it has to maintain its frequency. Pi electrons moves onto the oxygen, O minus, it combines with H plus, it becomes ol form. This is lactam, this is lactim. Last variety of structural isomerism which an organic compound exhibit is metamerism. The metamers are those compounds in which the carbon atom attachment around a divalent or a polyvalent functional group differs. An example which we can give is oxygen ethers and sulfur in thioethers. The chain length on either side differs. diethyl ether or ethoxyethane, there is an divalent functional group, that is oxygen. Here the ethyl group is attached on both the sides. In methoxypropane is the metamer of ethoxyethane. In this, propyl group and methyl group is attached to the divalent oxygen. Here in ethoxyethane, two ethyl groups is attached to the divalent oxygen. Methoxypropane and ethoxyethane are metamers. Pentanone, here two pentanone, here methyl group and propyl group is attached to carbonyl, and pentane 3-one, two ethyl group is attached to carbonyl. This is pentane 3-one and pentane 2-one are metamers. This is all about the structural isomerism that an organic compound exhibits. The next presentation, let us look into the configurational isomerism. Till then, have a nice day. Thank you.